For the eigen, so I say we are going to do eigen or eigen vectors. This one is a name, eigen vectors, and then eigen values, eigen values. So what happens is here is that it's a concept for vector spaces where we actually so let's say we have a point 2 3. So this is a point in a 2D plane when we are dealing with 2D plane. Then you know that sometimes you can scale this in up by a value. You can scale this in by, let's say, multiply by 2, then it will scale up to give you 4 6. So this is the scaled version. So this is a scaled version, and then you use this number 2 to scale it up. So there is a final one, and then there is a distance, a particular value that we use to multiply. So what we are trying to do is to get, so here it's going to happen in the world of metric. What we have here is just a 2D plane, but we can have dimensions of, I mean, matrices are of different dimensions of like 2D plane, 3D plane, 4D plane, 5D, 6D, and all that. So we should be able to scale vectors in such manner. So we use matrices to scale them. So when we are doing that, we try to find, when we multiply that matrix by that vector, what value does it tend to? What value does it actually multiply by? What factor actually multiplies it? For example, let's say we can have a matrix A, and then we have a vector x. So let's say a vector x like this, right? So we know that vectors, we write them like this, top down. Let's say 2 3. So this is a vector, and then I have a matrix. I may have a matrix. Let me clean this side. So like the matrix, let's say 1 2 3 5. So this is a particular matrix.
Have you start for long?
Can you start? Jerome just joined, so if you can maybe start over.
No, he just started, so maybe you can start over.
Oh, all right.
I will send you a message, but you didn't respond.
Oh, really?
Yeah,
Oh.
just right now. I could not tell some more.
Oh,
About someone, your friend, cover them assignment there. My work session at the video tab.
okay.
Let's take a 10 minutes round. That'll come over clinic here.
I think I'm more again.
Oh, I don't know. Everything is about money, so I don't know. I'm gonna expect not very much so much.
Okay.
By next week, I have to be in Apula by all means. By Sunday, I have to be in Apula.
All right. For the yellow card.
Our yellow card over now, over 100 cities.
At least
But they gave me receipt too. On receipt.
Okay.
The money about the serious no one, sir.
So I was giving the analogy that in a 2D plane, when we have the x and y, let's say we have a point 2, 3. So when we want to do the transformation or transform these points, we can either scale it up or do whatever transformation that we want to do. So if we want to scale it up, we can usually, for example, multiply this particular point by 2. Then that will give us 4 6. And then if you do that for 6, this is a new point. So we'll be able to scale it by a factor or by a number. So this is happening in 2D plane. But there are times that we actually want to scale a particular vector by, you remember when we were plotting points, we try to change it into vectors like this when we're plotting points. So now we can use matrix in order to scale or transform vectors. You can use matrix to transform vectors. So those vectors that are being transformed by a particular matrix, or yes, if you have a particular matrix, it has some group of vectors that it can be used to scale with. those vectors are called the Eigen Vectors. And the scalar value, that is actually the scalar value that allows to use that matrix to be able to transform the vector. That was called the eigenvalue. So the eigenvectors are the vectors. The eigenvalues will turn out to be the values that we actually use to multiply at the end. So we'll be confirming. So in this case, we'll be trying to solve questions to see if a particular matrix, a particular number is an eigenvalue, or a particular vector is an eigenvector for such a matrix. So we'll be given the matrix, we'll be able to confirm if a particular number is an eigenvalue of that matrix, or if a particular vector is an eigenvector of that matrix. So those are the things that we'll be dealing with. I mean, that's what I.
Come again.
So basically, because I say that for matrices, what we know initially is just x and y, 2D plane. But there are greater dimensions like 2D, 3D, 4D, 5D planes. So to do those transformations, you don't need these 2D plane things again. We usually use matrices. And for these matrices, in order to, so what happens is that they are used to transform or maybe scale up various vectors or various points in a space, or in a vector space. So what happens is that for each matrix, for a given matrix that we have, you need to find the eigenvalue and the eigenvectors. So a matrix you should be able to dictate or confirm or maybe validate if a particular number is an eigenvalue for that matrix or is an eigenvector for that matrix. So it's two things we are going to do that from just one matrix, right? Either the value or the vector. So we all call them the eigenvalues, or we call them the eigenvector. So I mean, sometimes it's by solving it that we get to understand that. But basically, that's the general info that we are trying to get. So for this example, like 1, 2, 3, 3, 5, eigenvalues are actually just one number. They are just one scalar number that you have. Like 1, 2, 3, 4. They are just single values that you get, just like how we found rank. But yeah, they are also single values. So for this particular matrix, for example, they can ask you to confirm if 3 is an eigenvalue of this matrix. If 3 is an eigenvalue for this matrix, it's as an example. Or if this vector, if you think that this vector is an eigenvector of this matrix, something like that. So you follow some procedures in order to arrive at that, or you follow some procedures to be able to confirm that particular thing. I hope that's okay.
Yeah, I think with the example.
All right.
Because me, I didn't get anything. Let me take the example.
All right. So now, I have a particular matrix. Let's say you have matrix A equals to 1, 6, 5, 2. 1, 6, 5, 2. And then we have a vector mu. So we are going to write it this way in this case because we are going to be using it to write with matrix. So I'm going to have something like this. In the textbook, is the V is actually this U and V are actually bold. So this one is 3, -2. But we know that vectors are written horizontal. No, this is vertically. But matrix, we know that these are their rectangular or square. All right. So we have this matrix, and then we are going to confirm if U and V are eigenvectors of this matrix. We want to confirm if U is an eigenvector for this matrix or V is an eigenvector for this matrix. That's what we are going to do. So by eigenvector, it means that you see, when I was giving this example, I gave 2, 3, and if you scale it up, you have by 2, you have 4 and 6. So this one, so this particular value that we use to multiply at the end is the eigenvalue. I mean, in essence, it's an eigenvalue. So we are trying to find if there exists a particular number, whole number, such that when you multiply it by that particular original vector, you will find a scaled form. That's what we are trying to look at. So this is the eigenvalue, right? So the eigenvector is that such a way that, okay, do we have any particular number that when we multiply by that through that matrix, we should be able to have our original or a scaled form of our original vector. So right now, what we have here is that they have given us the matrix and they have given us two vectors. So we are going to take them one by one. We are going to take u first and see if u is an eigenvector of this matrix, meaning that for it to be an eigenvector, we should be able to find a particular value that will be used to multiply to find, that will be a scale factor of the the u. Let's start. So to do that, you have to multiply matrix A by matrix U. You need to multiply them. So you remember how we do the multiplication. We have 1, 6, 5, 2 against U is 6, -5. So you can see that this is 2 by 2 against 2 by 1. So you can see that it's 2 by 2 against 2 by 1. So this multiplication is possible because the ending here is the beginning of this one, and the resulting matrix will be 2 by 1. So we know that it will be 2 by 1. 2 by 1. That will be 2 rows, 1 column. So we will have 2 by 1, something like that. So we need to do this multiplication.
Okay, so we are just multiplying the A U, right?
So should we do it ourselves?
Times 6 will be 6.
Yeah, I'm looking for the answer because we've done it already.
And that will be 6. And the first one will be 6, right?
You mean the top here?
No.
I'm just looking for the values here, top and down.
And that will be 6 and 30. Oh.
6 and 30.
6, no, 6 plus 30, so 36.
The top is 36.
6? No, it will be 6 plus 36, so 42.
Someone says 42. Please take your time and then do the multiplication. So it's this matrix against this. So you remember you multiply this by this and this by this, then we add them. Remember this is -5.
Row against column.
Yeah, row against column. Element wise operation. So we are going back to what we learned at the
I think
beginning.
I'm getting my multiplication right off.
Oh, but what do you have? So what you are supposed to do is
I was rather using the scale factor rather. Oh,
it's 1 times 6 plus.
that will be 6.
What do you have?
Then 5 times 6 times 5, right?
It's -5 here.
Yeah.
It's -5. It's not 5.
So 24.
Yes, 24. So 6 minus 30. That will be -24.
Okay.
Yeah, so we are going back to what we learned. Right now we are going to be using everything we spend time on learning. So let's follow the same thing to get the bottom one.
5 times 6.
20.
Yes.
Is that the answer or is
Yeah, the answer.
someone got 20? Please, let's confirm.
There's 20.
All right. Brother Jerome, did you also get 20 or I should solve it?
This time is this. I'm coming. I'm begging
Alright.
use calculator. This was one thing.
So it's 5 times
I'm doing
6.
2 things at the same time. That's the problem.
Okay. Then into plus -5 times
Yes,
5.
that would be
That'll be 30.
I think it's,
30.
Am I 5 times 6 and
It's
2?
two.
It's 2.
yeah.
2.
So
So 30
2.
minus 10. That will be 20.
Yeah.
Alright. So it's actually 20. So we got this value. Remember, we are just getting u, a and u. So we have -4 and 20. Now let's look at 6 and -5, right? We are moving from 6 -5. After passing it through u, through a, we have -24 and 20. Do you think that there exists a particular number that when you multiply u by, you will get this negative 24 and 20. We are looking for that particular factor. That is
Yes,
once
4.
it's what?
Yeah.
4.
Says for 24.
Are you sure it's 4?
4. Yes.
Oh,
I'm not sure it's 4.
If you multiply 4 by 6, you get 24. If you multiply 4 by 20, by 5, you get 20.
Yeah,
Okay,
yeah,
but it's negative. Negative 4.
yes, it's actually negative 4. So we can see that we have negative 4 and 20, negative 24 and 20. And looking at the u and then the final answer after passing a against u, you have this. Look if there's a number that exists that will give us like a whole number that will give us a scale form, a
mm,
factor or something. Then right now we have negative 4. So you can see, you can now conclude that yes, because we have found this in, so we have found an eigenvalue. This value is the eigenvalue. Eigenvalue. Because the u gave us an eigenvalue, therefore u is confirmed to be an eigenvector of the matrix.
Oh, I see.
Yeah.
I'm
So
so
when
sorry for taking you. I beg you, take it
yeah,
from me again.
all right. So you got up to this place, right?
Yeah.
Now we are trying to find. So you compare, you yourself, you compare to see if there's a particular value that we move from u to this negative 24 to it. Is there any value that we got? And after our analysis, we realize that when we multiply u by negative 4, you have the top to be negative 24 and the down to be positive 20, which matches. So negative 4 becomes that value, that value that allow, that's for the transformation. Then so that particular value that we get, right? That value is called the eigenvalue. That value that we got is eigenvalue. Then it's just confirming that since we've been able to find an eigenvalue after doing this particular operation, therefore the u is confirmed to be an eigenvector of this matrix. Because we were able to find an eigenvalue at the end of the day.
Okay, so if let's say we were having the AU to be, let's say, negative 26 and 20, we would have, that is negative 26 and 20. It means we will not have had an eigenvalue.
Yes, it will be very hard. You will not find it.
You will not find, yes.
Yeah. So it's not, so u is not
So
an eigenvector.
it's not an eigenvector. Okay.
Yeah. Rajaran, do I need to go back again?
No, I mean, at when you reach the negative 24, 20, you have to use your brain, Abi.
Yes.
Senior man that.
All right. So when you get, because you're able to get an eigenvalue, therefore u is confirmed to be an eigenvector. Let's try for v. Let's try for v. So
So
I'm going
we'll
to
do AV.
yes, we'll do av. I'll keep this one. I'll go and do av here. So it's still 1, 6, 5. Remember the order. The matrix come before the vector because of the
Okay.
position. You know, if you switch it, it will be a two by
Not the same.
2 by 1 against a 2 by 2, which will not work.
Which will not work. Okay.
And we are looking for the result here. They have to rely on you.
Which one? Okay, another one. AV 1, 6.
so
Five.
negative 9 and 11.
Negative 9 and 11. Someone got negative 9, 11. Let me use blue this thing so that.
I'm coming to do it now.
All right. We are waiting for confirmation.
This is 3.
12.
This
That one
is
had
12.
3 and what?
Negative 12. Oh, we are not done, no, please.
All right.
So the second one, 12.
So it's negative 9, negative 9, and then 11.
Negative 9, negative 11.
Yeah.
Someone had negative
So
9,
that's the
negative 11.
that is no negative 911. No,
Positive 11.
not yeah, positive 11.
We
So
are
that's the
meeting.
same answer.
All right. It's left with Brad Jerome. Let's see.
Oh, I'm done. No, there's the same thing. Negative 911.
Okay. So can you find an eigenvalue? So let's compare this one. Can we have an eigenvalue?
So you use 3.
No, you can't.
No, we can't.
All right. So what does this tell us? It means that V is not.
An eigenvector of the matrix.
Yeah, that's it. So I mean this is the first scenario of the things where you just multiply and you get your eigenvalue. Okay. Now the next thing is they will now give you the eigenvalue and they will ask you to confirm if that particular value is an eigenvector. Hey, sorry. They will give you a particular value like 5 and ask, do you think that 5 is an eigenvalue for the matrix? Yes or no, something like that. So that's what you have to confirm. That's something that we need to go through again. You need to confirm if a particular given value, eigenvalue, you are just going to confirm if it is part of, if it is an eigenvalue for that particular matrix. So we are going to use the same matrix, and the thing that they give us is 7. The number they give us here is 7. We are going to use the same matrix. So can I clean?
Yeah.
So we are going to keep the same matrix. So we have done, they give us the vectors, we are to confirm it. But now they give us the eigenvalue and we need to confirm if we think that that particular so this is the same matrix that we are getting, and the eigenvalue, this is the symbol for it. We use the sigma. Is it sigma? No, this is not sigma. Lambda. This is the lambda sign. So we use the lambda sign for it mostly. 7. So we have to confirm if 7 is an eigenvalue for this particular matrix. So I will go. All right. So we realize that if you have a particular vector, any vector at all, let's say x, you multiply by a matrix, it should equally give you a lambda times that vector. So this is what we're looking for. So when we multiply this in by that, you realize at the end of the day, so when we had the negative 24 and 20, we could rewrite it as the original matrix is negative 4 times, I think it was 6 and negative 5. So this was this form. So this is the original matrix, let's say U or X. And then there was a lambda value like that. But we started from AX is equal to lambda X. So this is the general formula, right? When we start. So whenever you are finding an eigenvalue or eigenvector, this is the general equation. So there should exist a particular lambda such that when we multiply the matrix by a vector, it will be equal to that lambda times that vector. Then we get the same thing. So that's the general formula. But right now, they've given us the eigenvector. So what we need to do is that, so we are going to go to some small mathematics. That's like just proving. But it doesn't really matter. When we are done through the process, the next stage is how to show you to move on faster. So what we do is that we do AX. I'm going to move the lambda x to this side equals to 0. Equals to 0. So I just move this one to the other side. So equals to 0. And we need to factorize x out. We need to factorize x out. So just like how you have, I can have 2x minus x is equal to like 2. Then this one will be
And
X
uh-huh
out.
x2
out,
minus
right?
1.
X times 2 minus 1.
So x out 2 minus 1. But what happens in matrix, in the world of matrix, is that matrix comes before vector. Matrix comes before vector. So it's supposed to be written like 2 minus 1 and then x. Right? That's what's going to happen. That's what's going to happen. So what we have going to do is that we will have A minus lambda times x equal to 0. So I move from here to this side. Matrix, this side is the matrix side against the vector. So matrix come before the vector, even when we're writing the AS. And so we need to keep that order in mind. All right. But there's something missing. There's something missing. You see, when we are having 2 minus 1, 2 is a scalar and 1 is a scalar. So 2 minus 1 was possible. But if you look at this place, it is a matrix against a scalar. We don't have anything like that. For matrix subtraction and addition, we say that the matrices should be of the same size or the same dimension. So if it's a 2 by 2, it should be against a 2 by 2 and something like that. But this is a scalar number. So there's something that we need to keep in mind. We are going to bring the idea of when you do factorization of matrices like this and you want to bring it up, what happens is that you need to keep in mind identity matrix. So we know that when there was nothing here, when I have 2s minus x and I factorize x out, so you can see like 2 minus 1. So if I remove x here, nothing will be there, nothing will be there. But then there was 2 here, so I just kept the 2 minus. In multiplication, the identity for identity, like the identity element is 1 for multiplication. So generally that's it for multiplication. I don't want to go into those stuff. So in matrix operations as well, we also deal with identity matrix, which we talked about some time ago. So, and we say for identity matrix, only the diagonals are. So let's say if it's a 2 by 2 identity matrix, if it's a 2 by 2 identity matrix, so we have 1 1, every other place is 0. The diagonals are 1. The diagonals are 1s and every other thing is 0. And it should be a square matrix always. So this is what I have. I can have a 3 by 3, 2, 3, and then this is 0, 0, 0, 0, 0. So this is an identity matrix, but it's for a 3 by 3 matrix. Okay, so that's what we need to keep in mind. The reason why we are bringing the identity matrix is because we are having a matrix minus a scalar, which shouldn't be the case. Which should not be the case. So you need to make sure that when you are doing factorizing a vector from a number, you realize that it's a matrix against just a single number. Identity matrix will always be in your mind, that it should be the ones who help you make sure that the operation, because matrix can only subtract from a matrix. So in this particular case, you have to look at what identity matrix am I going to bring. It depends on the matrix. So the original matrix is 2 by 2. So you need to make sure that you bring a 2 by 2 identity matrix.
Identity matrix.
So it will become A minus your lambda value that you have. Again, because it's 2 by 2, this is 1 1 0 0. You remember that we use a scalar to multiply a matrix, right? So a scalar to multiply a matrix. You remember?
Yeah.
So that means that we're going to use that scalar to multiply each element. Do I need to go over something because we are just moving forward? Or maybe let me finish first.
So my only confusion here is that I was thinking the 2 by 2, that's the identity matrix, will replace the lambda altogether.
Oh no. You see, when I have this number 2, right? There's for this multiplication, right? But you know that this 2 is the same as 2 by 1. There's always an identity matrix. Identity element there. But
okay, so identity matrix is like 1.
Yes.
Okay.
Like
I
1
get it.
for matrices.
Okay.
So
in other words, how to write 1 can be in the 2 by 2 is this way.
Yes.
1 0 0 1. Okay.
Yeah. Let's say we were having this same equation, but we were having it like this: ax minus x equal to 0. Then I want to factorize x out. But this A is a matrix, so we're having A minus. Remember, we are taking someone will have written 1. Someone will have written 1 because I mean, X is going out. But for identity, for
Yeah.
the word of matrix, we don't do that. So you just do I, capital I.
Uh, okay.
I is for identity matrix. That's it. I mean, we reserve I for special symbol I for identity matrix. But the rest can be A, B, C, D, whatever matrix you want to label them. But I specifically is for identity matrix. And that identity matrix, you can adjust it. You can bring it in because the matrix that we are having is just 2 by 2. So we are bringing a 2 by 2 identity matrix. If it's a 3 by 3, we are bringing a 3 by 3 identity matrix. If it's 5 by 5, we are bringing a 5 by 5 identity matrix. That one is very flexible. So you have to just select it to match what you are subtracting or adding to. Right? Okay.
Thank you.
Welcome.
Francis.
Yes.
So I'm sure that you are just trying to prove this formula for us, right?
Yeah.
Proving a formula. So what are we trying to arrive at after this stage? The A minus is it the lambda multiplied by the X is equal to 0. So
I think he will just
okay.
he will
So this is
substitute
the final destiny or what?
No.
he will substitute the matrix into the A.
Yes.
Or
So okay, let me just go over this quickly and come back. So we finish first, then you see the entire picture. So we move from this general formula, then I just move this ones to this side. I got this.
Yeah,
But
but
over here, I need to factorize this guy out. So now I have this. But because I factorize this thing out, it's a matrix against a matrix. I'm supposed to bring I here. But if I bring this I there automatically, it's as if I mean you guys will not get me. So I had to explain why I will bring the identity matrix there.
Yeah, so because it is like subtraction addition, you're supposed to get a square matrix so that you can be able to do the subtraction.
Thank you. Yeah. So we need to actually make sure that our A is what? I think our A is where are you?
1, 5.
1652
1652.
minus our lambda. Our lambda is 7 here. 7. So identity matrix will be a 2 by 2. 1 0 0 1.
1001.
X vector equal to 0. But if you write this one again, I'm going to have 1652 because it's a scalar against a matrix. It's going to be 7 0 0 7. X equal to 0. Do you remember?
Please kindly relax a bit.
Oh yeah, I'm just expanding it so you can have a look at it again.
Yeah.
I'm just using this scalar number that we use to multiply. Remember, I did something in the beginning. 2 8.
Yeah.
So it's 7 multiplying inside.
That's fine. Yeah.
All right. So now we need to do this addition. I mean subtraction, because we explained that for matrix subtraction, it's just like direct element by element.
Yeah. Element by element.
1 minus 7, that will be negative 6. 6 minus 0, that will be 6. 5 minus 0, that will be 5. And 2 minus 7, that will be negative 5. Yes. So we have this against this vector equal to 0. All right. All right. Now we are at this stage. Now. This is where we are going to use we need to form an augmented matrix from this. For the augmented matrix, you see the other side is 0, right? So we just fill in where should I go to? Let me go here. So we had negative 6 6 5 and negative 5. I have x equal to 0. You remember that when we had something like this, for like it's similar to this is the linear equation that we did, but that one we have to form the augmented matrix. So we focus on the augmented matrix now. For the augmented matrix, this side is now 0 0 0. So you fill every side with zeros. So it will be negative 6, 6, 0, 5,
0,
negative 5, 0.
5, 0.
So you just bring in 0, 0 here against it. This becomes the augmented matrix. Right? So from the augmented matrix now, you now do your REF. You do the REF, like row echelon form of your.
But why is the X not coming in the vector? The vector, why is it not coming? Or
Okay,
the vector is like the
x1,
S
s2, s3.
component that's multiply.
Yes,
Okay.
yes.
Okay. Okay. Thank you.
Yeah. So remember that when we had the system of linear equation, we just we ignore the s and we remove the coefficient and work with it. When we are
Yes,
done, we
yes. I
wind
just
back.
wanted to be sure because I didn't know that it's a vector.
All right,
It can be like that.
all right, all right. So now we have to find the REF of this.
Okay.
I mean, you see, in one operation, we had to use everything that we learned.
So we
R.
can multiply the row 1
Okay, at this point,
by
there,
5.
I will just be looking for the final answer.
Okay, okay, okay.
Mm.
Then that's fine.
So we should find what?
The REF, row echelon form of this augmented matrix.
Zero, zero, zero.
So 0, 0, 0,
Ah,
So negative six,
negative
six,
6, 6,
zero,
0,
negative
zero,
0,
6,
zero.
0,
6, 0, 0, 0,
0, 0,
0.
0, 0. Yeah.
Oh, all right, all right. So now, having a look at this, do we have a free variable inside?
Yes.
Yeah,
We have a free variable here.
yes. Which is what? X what?
X2.
Francis, sorry, I went up. What did you say?
I asked if you have the free variable.
Oh, okay.
Is it yes or no?
So I'm saying yes.
Yes. And which one?
I'm saying it's the second row, so X2.
S2. Do we confirm? Is that correct?
0x2 is equal to 0, so it is a free variable.
So S2 is a free variable. All right.
Yeah.
So yeah, so we have X1 here and we have S2 here. This one we ignore it. And then we know only S1 has a pivot. I mean, and S2 does not have a pivot. Those that don't have a pivot, we call them free variables. So for that matter, yeah, S2 is a free variable. So because we have a free variable in the augmented matrix, therefore the value that we started with was 7. So 7 is an eigenvalue. That's what you have to do. So when they give you the value, you try to generate the augmented matrix, and then you confirm if that particular augmented matrix has a free variable. If it's a free variable, therefore it is an eigenvalue. If it is not, then it's not
Just
an
like that.
eigenvalue. Just like that, that's it. Just like that. That's it. So uh,
One operation, see the plenty things we've done.
you can give this question and just put like 10 marks on it because you have to go through the steps. But yeah, let's go back to some of the things I know. I was explaining. So something like this stage, you can easily go and generate the. The thing that matters now is the eigenvalues, right? So if they give me a question like this, So when they give us a question like this next time to solve, what we'll do is that, hey, and you mentioned me a charge you. All right. So what we have to do is that, so because I know that is the eigenvalue that will matter, what I will do is that I will do 1652 minus 7 times the because it's 2 by 2, I will say 1001, and then equal to 0. So when I'm done combining, then I'll do the augmented matrix and proceed. I don't know whether you follow. Like, this is what
Yeah.
matters. So you get the original matrix minus the eigenvalue times the identity matrix. Identity matrix depends on the original matrix. Then you go to 0. When you are done doing this operation, I think you will have the negative 6, negative 6, yes. 6 minus, yeah, 6,
60.
5, negative 5. Then I just bring the 0 here, and then I'll focus on this matrix to find if I'll do the REF for this matrix and find if it has a free variable or not.
Mm.
Then we are done. But I was
Okay.
explaining the whole process in the first stage. I'm pausing to just take
So
concern.
you know,
Concern.
initially I wanted to even ask you that so this plenty addition and subtraction and those plenty operations we did, how would we use it? But this one has showed me that, Charlie.
All right, all right. Okay, so what do we have for the? Let me go back to this place. So we had this. Right, Jerome, do I need to go back somewhere?
You, let's continue. I'm confused, but let's continue. It seems
Which
like I'm
side?
not following.
Let's clarify it at once. Which side, so that we clarify it at once?
Uh, After the augmented matrix, that is 6, negative 656, negative 500, right?
Yes.
Then from there you find the.
REF, row echelon form.
Oh, okay. So which number did you use
For what?
to get the 00?
No, we multiplied row 1 by 5 and row 2 by 6 so that we can change the row 2. Because we want to get the first column to be
It's
30,
okay.
30. Yeah,
Yeah,
okay,
it's
sure.
okay.
All right.
All right.
All right, let's continue.
Yeah. But you know that someone could also get this negative 1, 1, 0, 0, 0, 0. It's the same thing.
Yeah.
Yeah.
That's fine.
Like if we express it, it will be x negative 6x plus negative 6x2 is equal to 0. Then, okay, yeah,
Be the
be the
same.
same.
All right.
That means
But
the person has likely, like if you also use RREF, you will get the same negative 1, 1.
yes, yes, you get the same thing.
Okay.
Yeah.
So for the reduce, there we don't use it at all. You can just stop at the.
Yeah.
So at what point do you use the reduce?
I mean, when they ask you they ask me. I
So
used to
the
when
That
they
one they
ask
ask.
examiner can ask.
yeah, when they ask us, you can't do anything. They say use the RI reduce row echelon form to solve for this. There is nothing you can do.
Oh, okay.
But I think that if you have the REF and you simplify to reduce the RREF, it helps you to get those X4 X this thing. It simplifies it
Quickly,
for you
fast. Yes.
instead of the REF.
I mean, now you understand, so you can be flexible around it. Which one works for you then?
Mm.
All right. So I mean, okay. So we are going to solve another question. I'll give a matrix and I'll give you an eigenvalue. We have to confirm if that thing is part of it. I mean, if it is an eigenvalue. But so we'll be able to confirm that 7. I need to proceed. I really need to do that. I'll do this. I wanted to make it like, oh, let me just move on. I'm not touching everything, but this one, I need to really do it. After you confirm that you have this particular final one, they can ask you to deduct at least one eigenvector from it. We can deduct one eigenvector from this. So we need to actually look very closely. So we focus on the free variable. That's what we are looking for. The free variable is S2. So in this case, the only equation that you can write here is negative 6 S1 plus 6 S2 equals to
6x2 is
0.
equal to 0.
Then I can have my x1 equals to
X1 equal to
S2.
negative 6x2 divided by.
Yeah, I mean, I did it directly. So if you do it on yourself, so you get this.
Yeah. Yeah.
All right.
That's,
So what we do is that we always have to find the basic variable. This is a basic variable. We write it in terms of the free variables. So now we need to find a vector. So this is the free variable is S2, right?
yeah.
So the free variable, we are going to be writing the vectors. Vectors are written vertically. They are written vertically. So x2 belongs to which column? I mean, it's definitely the second row, right?
Yes,
S2,
please.
second row. So where the free variable belongs to, I mean the row that the free variable belongs to, you need to put 1 there. The row that the free variable belongs to, when you are writing the eigenvector, the row that it belongs to, you need to put 1 there. So we are writing the eigenvector from whatever we will have right now. So we know that by default, x2 belongs to row 2. So we are going to put 1 there.
Okay.
That's the first thing. Now, moving on to row 1. Row 1 belongs to s1. But then, if you look at row 1, what is the coefficient of x2 in that row 1?
This one.
1. So this 1, 1 is an eigenvector that you can deduct. I'll go over again. So what we did first is that we were able to confirm because there's a free variable. See, if there's no free variable at all, don't even bother.
So please let me ask one question before you proceed.
All right.
So if it was 2x1 is equal to x2, 2x1 is equal to x2. So it would have been.
No, you will make S1 the subject always. You remember?
No, so I was thinking because the free variable is x2.
So it will become half S2, right?
Okay, half x2 rather. Okay.
You have to make S1 the subject.
Right. So, okay, so in that case, when we are doing the eigenvector, it will be x2 multiplied 2 and 1, right? Or half.
It's half. The coefficient.
Is it not just half rather? Okay.
Half against 1. So you just pick the coefficient like that. I'll go over it again.
But what I want to understand is why are you making the x1 the subject?
The row 1 belongs to s1. So even yesterday when we were doing it, you remember that for each row we were trying to make.
Yeah. Okay. That's true. Thank you.
You're welcome.
Just yesterday and I forgot. Wow.
So we got the S2, but you know S1, this one is 1 because that's where S2 generally belongs to. We write 1 there. But now you go and look for the other rows, those that are containing S2, then you bring the coefficient of S there. If the S2 is not part of it, then that particular thing should have been 0. Because when the thing is not there, it means that it is 0 S2. So
Okay.
it should have been, the coefficient would have been 0. So I'll go over again. So everything that we did so far until we get the eigenvector, the augmented matrix, from the augmented we do the REF to get this. And from the REF, we realize that there's a free variable. Because there's a free variable, that's why we are proceeding. If there's no free variable, just say that 7 is not an
An
eigenvalue. Therefore, we cannot even
eigenvalue.
find an eigenvector.
Okay.
Right, but because 7 there's a free variable, so it is confirmed that there's 7 is obviously an eigenvalue. So we go and write the equations like how we did yesterday. So the last one, definitely there's no equation needed, but the top one, we just have 2 rows here. So we write for that row,
Yes.
and we know that for the row 1 it belongs to S1, so you just write that thing in that
In terms of X.
in terms of x1. Then you go back, then you now, so the free variable is s2 against this. So s2 belongs to row 2. So for that reason, I went to put 1 where s2 is supposed to be. So I put 1 there. But then for the other matrix, which is the top row, which is for row 1, I just go and pick the coefficient of the s2 there. After making s1 the subject in that, I just pick the coefficient as it is and I place it there. Then I have half. I mean, it was not half, it was 1 though. In this case, it was 1. So we'll solve another question to solidify it. Don't worry. I think I need to solve the next one. Then before, I will solve the next one with you guys again. Then I'll give the questions out. So they can ask you to find, instead of saying that find the eigenvector, right? They can ask you to find one basis. So we can call it basis. This vector that we have half and 1, right? You can call it basis. Find a basis. So it's called basis. You can call it a basis or eigenvector. That's another name. And just if they ask and the question comes differently. It's a side note. Okay. So I'm going to clean this and then bring another question. I'll solve it fully again. We might because of this we might go beyond time today. Solve it again, give you one question to also try, then the rest will come later for you to try on your own. Then I think we need to. All right, so let's go to the first slide. All right, so now the question, the matrix that we have is 4, -1, 6, 2, 1, 6, 2, -1, 8. So this is the matrix that we have. And then the eigenvalue they've given us is 2. So let me do it like this. Eigenvalue they've given us is 2. So we have to find the basis. Or if the question can come, confirm if 2 is an eigenvalue, or find the basis, find the eigenvectors and everything. We are going to find everything. So because we've gone through the process already, we know that what we are supposed to have at the end should have been something like this. 4, -1, 6, 2, 1, 6, 2, -1, 8, minus 2 multiplying
0,
1, 1.
1, 0. Yeah.
So me, I like filling the diagonal first so that I will not get confused.
First. Okay.
So when we do this, these two multiply, enter. When these two multiplies and enter, because of space, I'll just replace the diagonal by 2. With 2, 2, 2. Then if I solve for this, That would be what? 4 minus 2. I think that would be 2.
So flying speed, so I'm
Yeah.
coming.
All right.
Francis is going speed, but
I'm writing. By the time I raise my head, no, you are somewhere else.
All right. All right. All right.
he's doing it like we are pro.
Oh, okay. It's fine.
So I'm here.
I've gotten it. Let's continue.
All right.
So you multiplied.
Yeah. So what I did is, I know you guys are writing with pen. So me, I'm writing on something that can erase. If not, I would have
Yeah.
repeated the same procedure. And then,
So
Yeah, so
two,
2, then 0, 0 throughout. Yeah.
so I want to just replace the diagonal by 2, just so that I save space. That's
Yeah.
why. All right. So it is 2, 2, 2. Now we do our subtraction, row by element by element. 4 minus 2.
Yeah.
That give me
Minus
2.
2.
-1. I think this one is -1 and 6 because they are all minus 0. This
Yeah.
one will be 2. 1 minus 2. That will be -1. Right. That will be 6. 2 -1. Hey, how is the middle one -1? 8 minus 2. That will be 6. Hey, what made
6,
it?
yeah.
Yeah. So after doing this subtraction
Of
and
them,
everything,
they are the same.
so you find the augmented matrix now. For augmented matrix, we just add another additional column, making it 0, 0, 0, as like that.
Yeah.
So 0, 0, 0. This is the augmented matrix. Then we find the REF. This is where I'll need your assistance.
Okay. Those are the. Okay. So this one we can simply okay. So let's subtract. So
Let me write the first one because I know the first row there is like that.
2 minus 1.
Now we 2 minus 2 is 2.
Is
This minus this will give you.
and this also, and then 6 minus 6 is also 7. And then I'll do 1 with 3.
And give them
6. So this will give me the 51 minus 1. 6 minus. What's this?
yes.
So it is 2 negative 6 is 2 negative 1 6 0. Then all is 0 0 0 throughout.
This 0,
So 0 0 4. That's also 0 0 throughout.
Oh, really?
Yeah.
Yeah, that's it.
All right. Okay. After finding the REF, the next focus should be, are we having free variables?
Yeah, S3 is a few variable.
2 free variables.
2 free variables.
We have, yeah.
S3.
So we have x2. X2 is a free variable. And then x3 is also a free variable.
Please, do we agree?
Hello, I'm in class and I'll call you back.
Yeah. S3 is got to a few variable.
So
I mean,
S2.
if it's up to everything.
Okay. So the thing is that look for the number, the variable that has a pivot. So only S1 has a pivot, which is 2.
Yes.
The rest don't have. So S2 and S3 are free variables.
Yes,
So
please.
that means that there is actually the 2 is actually an eigenvalue. That is a valid point. Now after confirming that,
Can you come again with the meaning of the free variable because it's getting me confused. I was thinking it's only 2, but you're adding 6 to it again.
no, the free variable,
Yeah.
the free variable are 2. I mean, they are two free variables, S2 and S3. So for free variable, right? So I mean, where should I go to? I was loading the yesterday's videos, but my YouTube was flagging some things, so that's why I couldn't send. I sent only for the other day. So for the free variable, please can I click this bottom one?
Yeah, you can.
Right. This were procedure stuff. So if we are to solve for this, right, we look for the from the bottom. So it will have been like 0 S3 equals to 0, right, from the bottom. Then
Yeah.
we realize that 0 times any number can give us 0. So that's correct. It's a correct equation. So you, no matter the value that you put over here, no matter the value you put, you give to S3, this equation will still be valid. Because S3 can take as many values as it can take. For that reason, S3 is a free variable. Because it's free, so you can supply anything for it. But the one like S1, you cannot just supply any value. It needs to depend on the free variables. So we don't, so free variables are like that. If you go to S2, for example, the second row, you have like 0 S2 plus 0 S3 equals to 0. So like we talk about S3 being a free variable already. So if you come to S2, S2 also, if you give any value as well, it's also be a free variable. Then yesterday I realized that, I mean, that's what I shared, that actually when you have the rows and then the rows that have a free variable, like the rows that have a pivot, so the pivot here is 2. Only the first row has a pivot 2. You see, like then it means that only S1 has a pivot, but the S2 and S3 don't have a pivot. Because they don't have a pivot, they are automatically free variable. That's another way of, I mean, identify the free variable without even going through that stress. So I mean, that's what we did with the free variable thing. But the actual concept was because we can supply as many any value at all to it, and our equation will still be valid. That's why we call them free variables. But to identify them quickly, we realize that when you think about the ones that have a pivot, then they are the basic one, and those that don't have a pivot are the free variables. Right, Jerome?
So the free variable in that matrix is what?
The free variables are, so you see that only S1 has a pivot, which is 2, but S2 and S3 don't have any pivot at all. So S2 and S3 are the free variable. S2 and S3 are free variables.
I thought you said 2 and 6. That's why I got confused.
Oh, 2 and 6. Oh, okay. Maybe you didn't hear me well. All right. So S2 and S3 are the free variable. So that one, we've concluded that. So because there's a free variable inside, even if there's at least one, we don't have to have like many. So S2 and S3 are free variable. That one has been confirmed. For that reason, the lambda 2, the lambda value that they say the eigenvalue 2 that was given us initially to work with this matrix is confirmed that this eigenvalue is actually valid for the matrix, because after doing the REF and everything, we realize that there are free variables, at least one. So right now we have 2. Okay, that's this. But now we need to find the basis or the eigenvectors. We now need to find the eigenvectors. So to find the eigenvectors, let's write the equation for those that are
Francis,
not.
please, can you hold on? I wanted to ask something.
All right.
So you see the row 3,
Yes.
the augmented, the last one, equal to 0. What if it is 15? So S3 is equal to 0, S3 is equal to 15. I know it is no solution, but I wanted to ask, so would you say that one is a free variable as well?
The thing doesn't
You
have a
get what I'm
solution
saying?
at all. So the whole system is
So because
inconsistent.
there's no solution,
They're inconsistent. The whole system is inconsistent. So it's no solution at all.
so it means that so would you confirm that the these two sign we could anything?
Eigenvalue.
Yeah, it is not an eigenvalue
It's
of the
not. It's
matrix.
not. It's not.
Okay, okay.
It's not. Thank you for that. I get your question. Thank you very much for asking.
Yeah, you can go ahead.
All right.
So do we write the basis for the x2 and s3 separately, or we combine them?
So that's what we are going to. That's what I want to write
Okay.
now. So let's go there and see when we get there. So we have to write the equations. We have 2x1 minus x2 plus 6s3 equals to 0. So the row belongs to s1. So I need to make s1 the subject. So because of space, I'll just do it quickly. But it's supposed to give us half s2 minus 3s3. This is what, when we make s1 the subject, this is what we are supposed to have.
Okay, Francis.
Yes,
So the free variable you're talking about, is it also part of the solution?
the free variable, yes, they are also part of the solution. So yesterday,
No,
when you had something
no,
like
I
that,
think it's just asking like the way you wrote it. No, it looks like it's part of the equation you are writing. That's
Not the equation, I mean part of the solution.
okay.
yes. Free variables are
Maybe
part.
the equation step by step. So I wanted to know, is
Oh
it
yeah,
also part of the solution?
yes.
So
So
how will you put it? In words or what? After getting the R,
REF,
yes, after getting that one, then you move to the free variable, which you
yes.
convert to be x2 and x3. So that one is it also part of the solution, or is just
Yeah, you say is that s2 and s3 are free variables.
then you continue again to
Yeah,
find the make the x1 the subject for the
yes.
first row,
So
x2 the
for the,
subject for the second
yeah,
row,
yes,
and x3 the subject for the third row.
yes. But the third row and this, they don't need any equation.
Okay.
Look, if you're looking at it
Right,
right now.
Jerome,
Yeah.
I think it's confirming that we are confirming that there are free variables to also confirm that the what two is an value of the matrix. I don't know whether I get what I'm saying. The reason we are confirming the free variable is because we want to confirm whether the two is an value of the matrix.
Okay. I think when I get yesterday's video and today's video and watch again, I'll be fine.
Oh, all right, all
Okay.
right. My bad, my bad. It's just this YouTube thing that's worrying me. All right. So yeah, where are we? We are here now. So we got this equation now. So now we need to write the basis or the eigenvector for s2 and the eigenvector for s3. We need to write eigenvector for s2 and eigenvector for s3 because they are the free variables. So they are the one that we write for. So I'll write s2, right? Like how I did last time. I mean, recently. Then what do we have? How many rows should we have? We have 3. Remember, we had 1, 2, 3. So we are going to have 1, 2, 3 things to put here. Then I said that we know x2 belongs to row 2. S2 belongs to row
Yeah.
2. So where it belongs to naturally, we need to keep 1 there. So we are just going to put 1 here. Let me be doing the one for S3 on the side. So S3 belongs to row 3. So I'm going to put 1 here. But this and this, I've not put anything here. So 1 and 1. Okay. Now, looking at S3, we are going to row 2. If you look at row 2, the coefficient of S3 is 0, right?
Yes.
So it will be 0. Because you don't even have an equation there. So everything is 0, 0, 0. So we just keep it there. Even for S2, if I come to S2, if I go to the row 3 for S2, it's not there. So I'll put 0 there. It's also not there. So 0 and 0. So S2 is not in row 3. S3 is not in row 2. So I'll put 0 there. Now, the only place where you have an equation is at the top, meaning row 1. Now, if you go to row 1, what's the coefficient of x2?
Half.
half. So you write that half here. Now you go to S3. What the coefficient of S3 there?
-3.
Negative
Negative
3.
3.
Yes. So the bases are these vectors, half 1 0 or negative 3 0 1. Half 1 0 or negative 3 0 1. You can even do multiples of them. I mean, it's a vector, so you can have like that one is a side note. I mean side note. This
Andrew,
one, yes.
so I want to just ask a question based on this.
All right.
So if we were just assumption or
All
if we
right.
were having like root 2, right? If the root 2 is not 0 throughout, but is maybe 0 2 0 0, that means yes, 0 0. That means that x2 is not free variable again, right?
Yes. Yeah, it's no more free
So it
variable.
means that we would have just concentrated on x3.
Yes.
Okay, so we would have done an equation for x2 as well.
Yes.
So x2 would have been 2x2 is equal to 0.
Yes.
Okay, all right. And even that is undefined. So
No, it's not undefined.
it's not undefined.
No. It's just like S2 will be equal to 0.
Okay, yeah. All right. Thank you.
Welcome.
All right. Okay.
All right. So we got these two bases, right? And they will ask you find the eigen vectors. So I was saying that you can write multiples of these. I mean, this one, if I multiply this vector by 2, I'll have 1 2 0. I mean this and this. They are just multiples of,
So
yeah. So you can write,
I can do multiple of 4.
yes.
So that will give me 2,
Mm-hmm.
2, 2,
Or 2 4 0.
4,
40.
0. Yeah. 4,
Yeah.
0.
But what
Okay.
we intentionally do smartly is that is to be able to eliminate if they contain fraction. We try to just we don't like fraction, so you just work around the closest one that will eliminate all the fractions in that particular vector.
Oh, okay.
Yeah, we just don't. It's not like it's wrong. The question is not wrong, but it's best to just have something like that. So these are the eigenvectors: 1 2 0 eigenvector, negative 3 0 and 1 eigenvector for the eigenvalue of 2. You know that you might know that if you pick a different eigenvalue like 3, we have to go through this whole procedure again. We might even find out that 3 is not even an eigenvalue, or we might find out that it is. But in that case, only S3 is not only S3 is free variable. If it's a free variable, we might have only one eigenvector.
Okay.
There's no
So
way
this
like
time around, eigen vectors are 2. So can we write it this
it,
or this or this and this, like in your conclusion?
or you write and this and this,
Okay.
put them apart. All right. So the one I'm going to give is just you confirming if a particular vector is. So we are just going to, for this one, we're going to say is 5 an eigenvalue of A. So I'll give the matrix. So the eigenvalue that I have for this matrix is 5. So then the matrix is A. You are just to confirm if it is an eigenvalue for this matrix. 1 3 0 5 2 2 6 2 2
So
6.
so we end at REF.
Yes, yes.
Okay.
This is why we should confirm one.
Confirm is 5 is an eigenvalue for A.
Okay.
Francis,
Yes.
I'm getting negative 5x3 is equal to 0.
Negative 5s3 equals to
Is
0.
equal to 0.
I mean, do you have your
Uh,
matrix? Maybe you can mention your matrix
yeah,
also.
Okay, my REF
Yes.
1 negative 3 1 0
Mm-hmm.
0 4 2 0
From 20, 00,
0 negative
negative
5 0.
5.
Okay. So this is what you have. Then
Mm-hmm.
Yeah, so
I want
negative
to know.
5.
I want to know if it's
Negative
an
5 is equal to 0.
Negative 5 x 3 is equal to 0.
It's
like.
So,
not a free.
Is
so
there?
Okay,
it's,
there is
it's
a pivot.
The question
There's
is,
a pivot, so it's not a free variable.
do we have a free variable?
It's not a free
there's
variable.
no
There's a
free
pivot.
variable. There's no free variable. All of them have pivots.
All of them have pivots.
Therefore,
Yes.
therefore, the
X have
lambda,
pivots. Yes, all of
therefore,
them
the
have pivots.
lambda of 5 is not an eigenvalue of the vector of the matrix.
Yeah, that's very correct. I mean,
Yeah.
Okay.
the matrix that you guys had to is exactly the marking scheme, and
Oh, okay.
yeah, they all
Nice.
have pivots.